Welcome to today's paper reading. Today's paper is titled, LLM in Context Recall is Prompt Dependent. This paper was published on the AR14 preprint by Daniel Machlab and Rick Battle from VMware NLP Lab. The proliferation of large language models, LLMs, underscores the necessity for comprehensive evaluations to understand their strengths, weaknesses, and ideal applications. A key aspect of this evaluation is assessing the model's ability to accurately retrieve information from a given prompt. This capability significantly affects how well the model can use contextual details, influencing its practical effectiveness and reliability in real-world scenarios. Our research employs the needle-in-a-haystack method to analyze the in-context recall performance of various LLMs. In this method, a factoid is embedded within a block of filler text, which the model is tasked to retrieve. We evaluate the recall performance across different haystack lengths and needle placements to identify performance patterns. Our study reveals that an LLM's recall capability is influenced not only by the prompt's content but also by potential biases in its training data. Additionally, modifications to the model's architecture, training strategy, or fine-tuning can enhance performance. This analysis provides valuable insights into LLM behavior, guiding the development of more effective applications. The advent of large language models, LLMs, has significantly transformed the field of natural language processing, NLP. These models have brought remarkable advancements in various applications such as text generation and machine translation. One of the key abilities of these models is their capability to retrieve and process information from the text input to provide contextually valuable responses. This process is heavily influenced by the model's context window size, where a larger context window allows the model to process more information at inference time. This is particularly important for tasks that require a deep understanding of lengthy texts, maintaining consistency over extended conversations, and integrating information across multiple sources. Reflecting these advantages, recent advancements in LLMs have seen a trend of increasing the size of context windows. For example, models like Llama 2 operate with a context window of 4096 tokens, while GPT-4 Turbo handles a context window of 128,000 tokens, and Gemini 1.5 extends this to an impressive 10 million tokens. However, to fully realize the benefits of a long context window, an LLM must be able to reliably recall information from it. Table 1 lists the 9 large language models, LLMs, evaluated in our study using the needle-in-a-haystack testing methodology. These models were chosen for their prominence in current research, variation in context window sizes, and availability. The table highlights the context window sizes for each model, which range from 4,096 tokens to 128,000 tokens. Our research investigates how these factors influence the recall performance of the models, particularly in relation to the length of the haystack and the placement of the needle within the text. As the variety of large language models, LLMs, increases, evaluating their capabilities becomes crucial for selecting the appropriate model for specific use cases. To address this, various tools and approaches have been developed, including benchmark leaderboards, evaluation software, and new evaluation methods. One such method is the needle-in-a-haystack approach, which evaluates the recall performance of LLMs by testing their ability to retrieve specific information from prompts. This method has been extended in this study to evaluate a selection of LLMs and compare their performance on various needles. Additionally, to streamline the evaluation process, automated grading using GPT-4 Turbo has been employed, significantly reducing the time and cost associated with grading 31,275 responses. Table 2 presents the factoid and question pairs utilized in the needle-in-a-haystack test designed to assess the recall performance of large language models, LLMs. These tests include 3 distinct scenarios: Pistachio AI, San Francisco, and Thornfield Hollow. Each scenario features a factoid embedded within a haystack of text, followed by a question that prompts the LLM to recall the factoid. This methodology allows for the evaluation of how well LLMs can retrieve specific information from various positions within a text prompt, providing insights into their recall capabilities under different conditions. The methodology involves constructing haystacks with varying lengths and needle positions to analyze recall performance. The haystack length is varied to test the model's recall capabilities across its context window, while the needle position is varied to assess retrieval at different prompt locations. The prompt structure includes a system message, a haystack with an embedded needle, and a question asking the model to recall the needle. Evaluation is conducted by scoring recall performance on a 1 to 5 scale and generating heat maps to visually analyze the results. This approach allows for a comprehensive assessment of the model's recall abilities under different conditions. Table 3 provides an example of a prompt and its corresponding successful recall response in the context of a pistachio AI needle-in-a-haystack test. The top section of the table shows the prompt given to the AI, while the bottom section displays the AI's correct response. This test is designed to evaluate the AI's ability to accurately recall specific information from a large body of text, simulating a needle-in-a-haystack scenario where the target information is difficult to find. Figure 1 illustrates the recall performance of GPT-4 Turbo in different needle-in-a-haystack tests. The top section shows the San Francisco test where GPT-4 Turbo scores 68.2%, indicating worse performance due to conflicts with training data. The middle section shows the Thornfield Hollow test where GPT-4 Turbo scores 93.7%, demonstrating better recall without training data conflicts. The bottom section shows the Pistachio AI test where GPT-4 Turbo performs perfectly. The heat maps in the figure provide an overview of the LLM's recall performance across various haystack sizes and needle placements, highlighting the impact of training data conflicts on recall accuracy. The recall performance of large language models, LLMs, is significantly influenced by various factors such as prompt variations, conflicts with training data, and the size of the model. For instance, a single sentence change within a prompt can alter an LLM's ability to recall information accurately. This is evident in the performance of GPT-4 Turbo, which performs perfectly on the Pistachio AI test but scores lower on the San Francisco and Thornfield Hollow tests. Additionally, when a prompt contains information that conflicts with the model's training data, recall performance is degraded. This is illustrated by the differences in recall scores between the San Francisco and Thornfield Hollow tests. Furthermore, increasing the number of parameters in a model, such as comparing Llama 2 13b to Llama 2 70b, can enhance recall capabilities. However, this also highlights the diminishing returns in performance improvement beyond a certain model size. Table 5 presents the recall scores for each large language model, LLM, on 3 different needle-in-a-haystack tests. The recall is determined by dividing the score the model achieved at each combination of haystack length and needle placement by the maximum possible score. Each model has the potential to score up to 5 points on each test. For instance, Llama 2 13b, which underwent 1,225 tests, could theoretically score up to 6,125 points. This table provides a comprehensive view of how well each model can recall specific information embedded within varying contexts. Figure 2 compares the in-context factoid recall performance of Llama 2 70b and Llama 2 13b. Llama 2 70b, with 5.3 times more parameters, demonstrates superior recall capabilities compared to Llama 2 13b. This figure highlights the direct correlation between model size and recall efficacy, showcasing Llama 2 70b's enhanced ability to recall factoids from context. In the analysis of GPT-4 Turbo's recall scores, anomalies were observed in rare cases due to specific placements within Paul Graham's essays. For instance, Mistral version 0.1 showed a 40.9% recall performance, significantly lower than Llama 2 13b's 94.1%. The heat map inspection indicated issues with text attention beyond 1K tokens. Mistral version 0.2, despite having the same parameters, improved its recall by altering the prompt. An example with Llama 2 13b illustrates a response scored 3 to 5 at 1,922 tokens, which, when grounded in the provided prompt, was deemed difficult to evaluate accurately. These findings highlight the complexities involved in assessing LLM responses. Figure 3 compares the recall performance of Mistral version 0.1, Mistral version 0.2, and Mixtral. Mistral version 0.1, shown at the top, has a recall performance of 40.9%, significantly lower than Mistral version 0.2 in the middle, which achieves 94.8%. Mixtral, at the bottom, shows the highest recall performance at 96.7%. This comparison highlights the improvements in recall performance due to architectural and training strategy adjustments in Mistral version 0.2 and Mixtral. The ability of a large language model, LLM, to recall information from the prompt significantly influences its effectiveness in generating precise and relevant answers. Our study using needle-in-a-haystack tests revealed that small changes in the prompt can significantly affect a model's recall performance. Additionally, the interplay between the prompt's content and the model's training data can degrade response quality. Enhancements such as increasing parameter count, altering the attention mechanism, using different training strategies, and fine-tuning can improve a model's recall ability. Understanding the variance in behavior of individual LLMs is crucial for identifying their strengths and weaknesses, which informs optimal application. In-context recall is one metric for evaluating LLMs, and continued evaluation will help in selecting the best LLM for specific use cases, thereby maximizing their impact and efficiency in real-world applications as the technology evolves. In this section, the authors acknowledge the support and contributions from several entities. Firstly, they thank the entire VMware NLP lab and the AI platform team for their support throughout this effort. Additionally, they express gratitude to Ramesh Radhakrishnan for reviewing the paper. Lastly, the authors acknowledge Darian Shetler for his valuable suggestions and guidance. No other contributors are mentioned in this section. Thank you for watching.